in the heart of Germany's industrial heartland, the Ruhr area, there stands a network of dams that played an indispensable role during World War II. These structures, strategically built to harness water for various purposes, were far more than mere barriers against floods. They were critical components in the German war machine's intricate machinery. The Ruhr area, with its population of over 5 million people and sprawling public transportation system, including trams and buses, was the lifeblood of Germany's industrial output. Embankment dams, which account for about 80% of all dams worldwide, were constructed across the region's rivers to create reservoirs that supplied water for both human consumption and industrial use. These dams were not just simple barriers, they were the backbone of Germany's military infrastructure, providing water for steel production and other crucial industrial processes. The Ruhr University Bochum, established in 1962, and other educational institutions in the region highlighted the importance of this area not just for its industry, but also for its technological advancements. It was these very dams that caught the attention of Allied strategists, who saw them as vital targets to disrupt German operations. Understanding the strategic importance of these dams is crucial for grasping why they became such significant military objectives during World War II. By targeting and breaching these dams, the Allies aimed to deliver a devastating blow to Germany's industrial capabilities and military infrastructure. This approach promised to slow down Germany's war effort, making it clear that these seemingly ordinary structures held extraordinary strategic value. Barnes Wallis, a British engineer and inventor, was tasked with designing these unconventional weapons. Known for his groundbreaking work in aviation, Wallis approached the challenge with precision and ingenuity. The bouncing bomb, also codenamed Upkeep, was designed to skip across water like a stone before sinking to the depth needed for maximum impact. Its unique properties made it an ideal weapon for the intricate task of breaching heavily fortified dams. Measuring 5 feet in diameter and 6 feet long, each Upkeep bomb was a formidable device. Spun backward at 500 RPM before release, the bombs weighed approximately 9,000 pounds, a remarkable feat of engineering for its time. In practice, these bombs were loaded onto specially modified Lancaster bombers. The planes would fly at low altitudes to avoid detection and release the bombs at precise intervals. The strategic planning behind Operation Chastise, as this mission came to be known, was meticulous. The bombers had to navigate treacherous landscapes and evade enemy fire to reach their targets. With each dam breach, the German war machine suffered a significant blow, slowing down its production of vital materials. The audacious mission underscored the strategic value of these seemingly ordinary structures. The development of bouncing bombs set a new standard for military innovation, paving the way for future tactical advancements. Their effectiveness in Operation Chastise remains a testament to Wallis's engineering prowess. As the war raged on, these technological breakthroughs would continue to shape the course of history. But for now, the focus was on the precise execution of a mission that could turn the tide. Before the bombs even left the ground, meticulous planning was underway for a mission codenamed Operation Chastise. The goal, to breach critical German dams using innovative technology. The target dams were strategically selected, the Möhne, Eder and Sorp dams. These structures were vital to Germany's war efforts, providing power and water control. The mission was set for the night of May 16-17, 1943. Flying Officer Guy Gibson led the operation. His expertise and cool demeanour under pressure were invaluable for such a high-stakes mission. The plan called for precise timing and coordination. With 33 crew members involved, each had a critical role to play. Tragically, only 80 of them would return from the mission. To minimise resistance and maximise impact, the bombers had to fly at a mere 60 feet above water level. This was lower than some church steeples in England. The mission required not just technological prowess, but also incredible human endurance and skill. The pilots had to navigate treacherous landscapes under cover of darkness. With the stage set for execution, anticipation built for what was about to unfold. The precise planning and bravery of those involved would soon determine the fate of the mission. 19 Lancaster bombers, each laden with a bouncing bomb, were the chosen tools for this audacious task. To avoid detection by German radar, these bombers had to fly at dangerously low altitudes over enemy territory. The Möhne Dam was the first target. A precise drop at low altitude would release the bouncing bomb. The bomb skipped across the water and hit the dam's face precisely as designed. With a mighty eruption, the Möhne Dam was breached, unleashing a torrent of water that would wreak havoc downstream. Meanwhile, the Eder Dam was targeted next. Another Lancaster dropped its bomb, which skipped perfectly across the water and struck the dam's face. The Eder Dam also gave way to the force of the bomb, causing a catastrophic release of water that would devastate nearby areas. Despite the success at Möhne and Eder, the Sorp Dam remained unscathed. The breach of the Eder Dam, though successful, had dire consequences. Released at a height of 60 feet, 18 meters, and speed of 240 mph, 390 km/h, the floodwaters surged downstream, causing significant flooding. The Ruhr Valley was inundated, and towns like Warburg were devastated by the sudden deluge. The swift onrush of water claimed numerous lives, highlighting the severe human cost of such a tactical strike. In addition to the immediate loss of life, the breach disrupted vital German industries and infrastructure, dealing a strategic blow to the nation's war efforts. The flooding downstream of the breached dams brought chaos to communities that relied on these waterways for their livelihood. As the waters settled, the true magnitude of the operation became evident, a testament to the audacious planning and execution that changed the course of World War II. The strategic impact of breaching the dams cannot be overstated. It hindered Germany's industrial capabilities at a critical juncture in the war. The mission's aftermath serves as both a cautionary tale and a strategic triumph, illustrating the high stakes and far-reaching consequences of wartime operations. For one, the operation demonstrated the potential of precision weapons. The bouncing bombs, designed to skip across the water and strike their targets with tremendous force, showcased the advantages of accurate targeting. This principle of precision has since been adopted in modern warfare, leading to the development of smart weapons that can strike specific targets with minimal collateral damage. Moreover, the technology behind the bouncing bombs has influenced advancements in aerospace engineering. The concept of using spinning projectiles to achieve specific effects has been explored further, leading to innovations such as spin-stabilized rockets. These rockets use rotation to maintain stability during flight, a principle that was first effectively demonstrated by the bouncing bombs. The precision and control exhibited by these weapons reflect the enduring influence of Barnes-Wallis's groundbreaking design. But the legacy goes beyond technology. The operation itself was a testament to strategic planning and execution under extreme conditions. The mission required meticulous calculations, precise timing, and incredible bravery from the pilots of Number Option 617 Squadron. This level of precision and daring has become a benchmark for military operations, inspiring future generations to strive for similar excellence. The enduring importance of this groundbreaking weapon lies not just in its immediate impact, but also in the lasting influence it has had on military strategy and engineering. The exact reason why the Sorp Dam withstood the attack is still not fully understood. Its unique design, which included a double curvature and an impervious core, may have played a significant role in preventing a breach. Another lingering question concerns the mission's planning and execution. The raid required precise timing and coordination among multiple bomber crews. The long-term impacts of this mission on the war effort are also subject to ongoing analysis. While it disrupted German industry and infrastructure, its true strategic value remains a topic of debate. As we continue to explore this historic event, it is clear that there are still many questions left unanswered. This mission serves as a testament to the remarkable ingenuity and courage displayed by those involved in shaping the course of World War II. The innovative use of precision bombing pioneered in this mission laid the foundation for contemporary warfare tactics. Modern military engineers and strategists draw upon the principles developed during this operation to refine their own approaches to challenging targets. The development of upkeep bombs, the bouncing bombs, demonstrated the ingenuity required to overcome complex obstacles. This innovation underscored the importance of adaptive and creative solutions in military technology. The low-altitude flight path taken by the Lancaster bombers highlights the necessity for stealth and precision in modern warfare tactics. This missions approach has been adapted to address similar high-stakes targets in present-day military strategies. The losses sustained during the operation emphasize the importance of meticulous planning and execution, a lesson that remains paramount in modern military tactics. The mission's legacy continues to shape the strategies and technologies employed by modern military forces around the world. The mission's success relied on precise calculations and innovative engineering solutions. As technology continues to evolve, how might future military operations further refine their tactics? Advancements in AI and machine learning could enhance situational awareness and decision-making capabilities on the battlefield. Autonomous systems might allow for more precise targeting and reduced collateral damage. However, ethical considerations and potential misuse pose significant challenges. The integration of hypersonic weapons, capable of traveling at speeds over Mach 5, could drastically shorten the time it takes to reach targets, making interception nearly impossible. This speed advantage would require sophisticated detection systems and rapid response capabilities from defending forces. Cyber capabilities will also play a crucial role in future conflicts, with cyber warfare potentially disrupting critical infrastructure without physical engagement. The convergence of these technologies could lead to more precise and strategic strikes that minimize civilian casualties while maximizing operational efficiency. On these occasions, veterans, families, and historians gather to reflect on the mission's significance in changing the course of World War II. These commemorative efforts serve to honor not just the tactical brilliance, but also the immense personal cost paid by those who carried out this vital operation. Anniversaries and exhibitions bring a sense of closure, allowing the public to appreciate both the strategic genius and the human sacrifice involved in such a pivotal moment in history. The enduring legacy of this operation serves as a solemn reminder of the strategic brilliance and personal sacrifice that can turn the tide in times of great conflict. Among the unsung heroes were the women who worked tirelessly at Bletchley Park, decoding German messages. Their efforts provided vital intelligence that helped plan and execute the operation. At airfields across England, women served as mechanics and support staff, ensuring that Lancaster bombers were in peak condition for their dangerous missions. Intelligence gathered by female operatives often went unnoticed, but was instrumental in guiding the bombers to their targets. In the aftermath of the raid, as news of the damage spread, it was clear that the operation had disrupted German industry and morale significantly. The comprehensive nature of the operation's planning became evident, showcasing how every component, including the often overlooked contributions of women, was critical to its success. In a war that was primarily fought by men, the strategic brilliance and personal sacrifice of these women remind us of the broad range of individuals whose collective efforts could turn the tide in times of great conflict. One of the most critical technologies that emerged was night vision. This revolutionary tool allowed pilots to navigate and execute missions under the cover of darkness. The early night glasses were primitive and offered very limited visibility, but they laid the groundwork for future developments. By the mid-1930s, more advanced night vision goggles were being developed, utilizing infrared technology to amplify available light. These new goggles allowed pilots to see in conditions where the human eye alone was useless, dramatically enhancing their capability during nighttime operations. Flying at low altitudes to avoid radar detection, these devices enabled the pilots to accurately locate and target the German dams. Without the advancements in night vision technology, such a daring and strategically significant mission would have been nearly impossible. The technological prowess of the RAF crews, coupled with their bravery and precision, showcased how crucial innovation is in warfare. The evolution of night vision technology continues to this day, with modern systems providing even greater capabilities for military and civilian use. During the height of World War II, the Ruhr Valley was recognized as the most significant industrial district in Germany, and arguably all of Europe. Its strategic importance lay not only in its extensive mining operations, but also in its robust arms production and munitions supply. The region's geographical location was also strategically advantageous. Situated inland and protected by nearby mountain ranges, it was relatively secure from Allied bombing raids compared to coastal areas. The region's mines supplied essential raw materials, making it a critical target during the war. Its strategic value was such that the Allies recognized that incapacitating these industrial centers could severely hamper Germany's ability to sustain its war efforts. Bouncing bombs required precision flying at low altitudes, which demanded an elite group of skilled aviators. This specialized mission needed the best of the best. Training was extensive and focused on mastering low-level flying techniques. Pilots practiced navigating treacherous terrain at night, simulating the conditions they would face over enemy territory. A key challenge was perfecting the release of the bouncing bombs at exactly the right height and speed. The bombs were designed to skip across the water's surface before reaching their targets. This meant releasing them at a precise altitude of just 60 feet. With a speed of 240 mph and spinning backward at 500 rpm, the timing had to be flawless. Any deviation could lead to disaster. Crews practiced countless times, refining their techniques until they could execute the mission with near-perfect precision. The dedication and skill of these pilots ensured that, even under immense pressure, they could carry out their daring task with remarkable accuracy. Wallis's background in engineering and aerospace innovations positioned him uniquely to tackle the complex challenges of wartime technology. He was known for his pioneering work on aircraft, including the development of the Wellington bomber. The design process for this innovative weapon was fraught with challenges. Wallis had to consider the physics of spinning projectiles and how they would interact with water surfaces. Wallis's ingenuity lay in his ability to marry theoretical knowledge with practical experimentation. He conducted numerous tests using scale models, refining the design until it met the precise specifications needed for the mission. His vision for the bouncing bomb was not just a technological feat, it represented a strategic breakthrough that could turn the tide of war. The tactical planning and scientific ingenuity behind this operation are testaments to Wallis's brilliance. The bomb, designed by Barnes Wallis, was an intricate piece of engineering. It required precise materials and a unique manufacturing process. Production faced unforeseen difficulties such as material shortages. Innovative solutions had to be found to overcome these hurdles. The effort and resourcefulness required to bring this innovative technology into reality were immense. It illuminates the behind-the-scenes work needed to achieve a strategic breakthrough. Its 4 Rolls-Royce Merlin engines provided reliable power and stability, crucial for maintaining altitude during low-level flights over Germany's defences. This operational prowess had been demonstrated in previous missions where the Lancaster showed remarkable reliability and performance under challenging conditions. Despite the challenges of flying at low altitudes and facing enemy fire, the Lancaster proved to be a dependable workhorse in the RAF's arsenal. Aerial photographs were particularly valuable, offering detailed images of the targeted dams, including their dimensions, surrounding terrain, and any defensive measures in place. These visual records allow planners to map out potential attack paths and anticipate challenges. Captured documents, such as blueprints or operational logs, provided invaluable information on the structural integrity of the dams and their water management systems. These documents were carefully scrutinized to understand weaknesses that could be exploited during the attack. Interrogations of captured prisoners, particularly engineers or staff involved with the dams, offered first-hand knowledge of their vulnerabilities and defenses. This human intelligence was cross-referenced with aerial data to build a comprehensive picture at each target. The gathered information was meticulously analysed in the planning phase, with engineers and strategists studying every detail to develop precise attack plans. They focused on weaknesses such as structural flaws or unanticipated water levels that could be exploited by the innovative bouncing bombs. Despite these efforts, collecting accurate information was fraught with challenges. German defences were robust, and enemy fire could disrupt reconnaissance missions. Nevertheless, the intelligence team persisted, recognizing that every piece of data was critical for mission success. As the Lancasters took off on their fateful night, the months of painstaking intelligence gathering paid off, showcasing the complexity and precision behind one of World War II's most daring operations. Early prototypes were simple spheres made of solid explosives. Tests showed that the bombs tended to disintegrate before reaching their targets. Wallis realized he needed a more robust design capable of withstanding the forces of high-altitude flight and the impact of hitting water. He experimented with various shapes and materials, eventually settling on a cylindrical bomb filled with high explosives and wrapped in a thin steel casing. Despite its sturdier construction, the cylindrical bomb still faced challenges. It tended to sink too quickly and exploded prematurely. Wallis understood that the bomb needed a way to skip across the water's surface before reaching its target depth. He introduced spinning into his design, reasoning that a rotating bomb could maintain stability and direction in flight. The challenge was finding the right spin rate. Too fast, and the bomb would fragment; too slow, and it would sink. Extensive testing led Wallis to set the optimal spin at 500 revolutions per minute. The final design incorporated a complex backspin that allowed the bomb to bounce across the water surface until it reached its target depth. The engineering feats behind the production of bouncing bombs, known as upkeep, were nothing short of extraordinary. The machinery required for their creation was both complex and delicate. At the heart of this process stood Vickers, Armstrong's factory in Cheshire, England. To achieve this, specialised lathes and milling machines were employed, capable of cutting the precise contours needed for the bomb's aerodynamics. These machines had to be calibrated with extreme accuracy, ensuring each bomb was identical and could perform as intended. The production process required a meticulous approach to ensure each bomb met the strict specifications. This included rigorous quality control checks at every stage of manufacturing. Any deviation from the design could potentially compromise the bomb's performance. In addition to the precision machinery, the unique materials used in the construction of these bombs were crucial. High-grade steel and specialized alloys were needed to withstand the intense forces involved in spinning the bombs at 500 revolutions per minute. The engineering challenges did not stop at mere production. The logistics of transporting these heavy, sensitive weapons to their launch points required meticulous planning and execution. Specially designed trailers were used to move the bombs, ensuring they remained stable and undamaged during transit. Success hinged on precise timing and environmental conditions. Weather reports were vital in scheduling the operation. Meteorologists scrutinized moon phases, wind speeds, and cloud cover to ensure ideal conditions for the bomber's low-altitude flight. Crucial to the operation was the presence of moonlight, which allowed pilots to navigate accurately and spot potential hazards. With no navigational aids, the bombers relied on visual cues from the landscape, guided by the subtle glow of the night sky. Alternative plans were in place for adverse weather conditions, but the operation's success depended on favourable skies. The intricate planning extended to every detail, including emergency procedures should the mission encounter unexpected obstacles. The operation's success highlights how environmental factors can significantly influence wartime tactics and outcomes. The breaching of the Eder Dam on May 17, 1943, was a pivotal moment during World War II that had far-reaching societal effects. The dam's sudden failure caused catastrophic flooding, wiping out villages and infrastructure downstream. Nearly 2,000 people lost their lives, many of them drowning in the ensuing deluge. The psychological trauma was profound, with survivors reporting nightmares and persistent fear of water. German authorities scrambled to manage the crisis, dispatching emergency services and establishing relief camps for the displaced. Yet, despite their efforts, the long-term societal effects were immense, altering daily life and reshaping communities in ways that would be felt for generations. Homes were destroyed, livelihoods disrupted, and the once thriving regions were left with a deep sense of loss and despair. In the midst of World War II, while strategic bombing campaigns focused on disrupting enemy infrastructure and morale, one operation stood out for its audacious technological prowess. At the heart of this daring mission lay an innovative technology, the bouncing bomb. The key to this incredible feat lay in the alloys used in the bomb's construction. Wallis chose high tensile steel for the outer casing, a material renowned for its strength and ability to withstand immense pressures. This alloy ensured that the bomb could maintain its integrity as it skimmed across the water's surface at high speeds. Inside, a complex mechanism of timed explosives and a spinning device called upkeep gave the bombs their unique bouncing ability. This spinning motion allowed the bomb to skip across water, avoiding obstacles and mines placed by the Germans. Once the bomb hit its mark, a secondary explosive would detonate, targeting the foundations of the dams with devastating force. One of the crucial modifications involved changing the bomb bay doors. Originally designed to open downwards for gravity-drop bombs, they were modified to swing out sideways. This change allowed the Lancaster to drop the spinning bouncing bombs at a precise height and angle, ensuring they skipped across the water's surface correctly. These modifications, while ingenious, also posed practical challenges for the pilots. Flying at such low altitudes over enemy territory required exceptional skill and nerve, especially with the added complexity of managing these specialized flight dynamics. Despite the technical hurdles, the pilots of No. 4, 617 Squadron trained diligently to master these adapted Lancasters and their unique handling characteristics. The modifications to the Lancasters and the innovative use of bouncing bombs changed the course of World War II, demonstrating the power of strategic engineering and daring execution. This mission highlighted not only the technological ingenuity of Barnes-Wallis, but also the unwavering determination and bravery of the pilots who carried it out. Precision bombing, which aims to strike specific targets with high accuracy, emerged as a response to the limitations of area bombing. Unlike indiscriminate area bombing, precision targeting required advanced technological capabilities and meticulous planning. The mission marked a critical shift in military strategy, demonstrating that precision bombing could be a powerful tool in targeting and neutralizing specific enemy infrastructure while minimizing civilian casualties. This immediate crisis not only disrupted civilian lives, but also dealt a blow to the morale of communities that had thus far remained relatively untouched by the war's devastations. The tactical success of the operation highlighted Britain's capability and resilience, a stark contrast to Germany's perceived vulnerability. The psychological effect rippled outward, sowing doubt among civilians about their nation's defences. Moreover, the loss of critical infrastructure hindered Germany's war effort by disrupting industrial production and hydropower generation. The dam's destruction led to a halt in factory output and delayed strategic materials, crucial for the war machine. Beyond immediate disruptions, the psychological toll lingered, with civilians grappling with a new sense of insecurity and fragility. This operation underscored the strategic importance of precision bombing and its ability to shift the tide not just physically, but also psychologically. Precision bombing technology was an evolving concept during World War II, shaped by the necessity to target specific objectives with increasing accuracy. Before the advent of advanced guidance systems, bombers faced challenges in hitting precise targets from high altitudes. Early bombing raids relied on manual aim and often resulted in significant civilian casualties. The development of the Norden bomb sight in the late 1930s marked a significant advancement, providing bombers with a more accurate aiming system. However, it still required manual operation and was limited by the human element. Barnes-Wallis recognized these limitations and began exploring alternative methods of precision bombing. His innovative, Upkeep bombs, known as bouncing bombs, were designed to skip across the water's surface before sinking and detonating near their targets. This new technology allowed for a level of precision previously unseen in bombing operations. The success of this operation demonstrated that precision bombing technology was not only possible, but could have a decisive impact on military strategy. The purpose behind the operation was not merely to disrupt water supply, but also to hinder industrial output by targeting key hydropower sources. The breaching of these dams had direct and indirect effects on Germany's ability to sustain its war production. The impact extended beyond just electricity. The flooding caused by the breached dams wreaked havoc on transportation networks, cutting off vital supply routes and making it difficult for crucial resources to reach industrial centres. Indirectly, the disruptions led to significant delays in production schedules as industries struggled to maintain operations without a stable power supply and unimpeded transportation routes. For example, the Ruhr area's extensive industrial complexes, known for their steelworks and coal mines, faced substantial setbacks due to these power outages and transportation blockages. The cumulative effect of these breaches underscored the vulnerability of Germany's infrastructure to precision bombing technology, a revelation that shifted the balance of power during the war. The impact on German war production was profound, leading to a cascade of issues that further undermined their military strategy and resilience. One key component of this innovative training was the use of simulators to practice low-level flying over water bodies. The crews trained relentlessly, mastering the art of flying just 60 feet above the surface, a feat that required extreme precision and control. This was no ordinary mission, and it demanded extraordinary measures. The Lancaster crews were not only tasked with navigating treacherous terrain, but also with releasing a specialized bomb, the Upkeep, at exactly the right height and speed. Every detail had to be perfected, from the spin rate of the bomb to the precise altitude at which it would be released. The Allied forces saw this as a turning point in the war effort, boosting morale and proving that innovative technology could outmaneuver traditional defences. For Germany, the breach highlighted vulnerabilities in their infrastructure, leading to increased defensive measures and a shift in strategic planning. The operation demonstrated that precision strikes could severely disrupt enemy supply lines and production, influencing future Allied strategies for similar high-impact missions. The bombs were dubbed Upkeeps and had a diameter of just 5 feet, but measured 6 feet in length. Spinning at 500 revolutions per minute before release, the bombs weighed a hefty 9,250 pounds. The backspin was crucial to making the bombs skip across the water's surface like a stone. This skimming action allowed the bombs to clear torpedo nets and other defensive obstacles. Once at the target, the bomb's spin stopped and it sank quickly to the depths. The precise calculation of the bomb's spin rate and weight ensured it would strike at the exact depth required to cause maximum damage. The dams, vital to Germany's industrial production and military capabilities, were seen as strategic weak points. The operation's success demonstrated the innovative and precise planning that went into its execution. Innovations like the backspin on the bouncing bombs would influence future military strategies. This daring approach would be studied and emulated in future military operations. To minimize drag and maximize maneuverability, each Lancaster was stripped down to its essential components. Non-essential equipment was removed, including the mid-upper turret, to streamline the aircraft for this critical mission. Navigation was another critical aspect. The pilots would rely on a combination of landmarks and sophisticated instruments to maintain their course. Any deviation could spell disaster, given the complexities of the mission. The crews underwent rigorous training to ensure they were prepared for any eventuality. This included practicing the release of the Upkeep bombs at exact heights and speeds, simulating the conditions they would encounter on mission night. Despite the audacious nature of the operation, every detail was painstakingly planned to minimize risk. The meticulous calibration of Lancaster bombers, combined with precise flight paths and rigorous training, underscored the intricate planning required for this pivotal mission. Military strategists began to envision bolder tactics, that could turn the tide of war. The psychological boost translated into a more aggressive posture in Allied battle plans. The breaching of the German dams signalled to both Allies and Axis powers that no stronghold was invulnerable. This realisation emboldened Allied commanders to pursue high-risk, high-reward missions. The psychological effects extended beyond the battlefield, influencing political and civilian morale. The audacious success underscored the Allies' resilience and determination. As the floodwaters receded downstream of the breached dams, a new sense of empowerment surged among Allied forces. This psychological shift would prove critical in shaping future military strategies. By breaching these dams, Allied forces aimed not just to disrupt water supplies, but also to unleash a catastrophic cascade of events downstream. The resulting floodwaters would inundate factories, destroy machinery, and bring Germany's industrial output to a grinding halt. The bomb, spinning backward at 500 RPM, needed to remain stable without prematurely exploding. Wallis and his team conducted extensive wind tunnel tests to perfect the bomb's spin and trajectory. One critical aspect was ensuring the bomb would spin correctly upon release from the aircraft, without prematurely triggering its explosive mechanism. The team used experimental aerodynamics to fine-tune the bomb's design, incorporating a spinning mechanism that delayed the trigger until the precise moment of impact. This innovation required meticulous calculations and numerous trial runs to ensure the bomb would behave as intended when released over water. By combining advanced engineering with precise operational planning, the British were able to execute one of the most daring and strategically important missions of World War II. Among these defences were torpedo nets designed to prevent underwater attacks. These nets stretched across the width of the dams, creating a physical barrier that would snare any incoming projectile. This method ensured that the bombs would avoid the nets entirely and strike their targets with maximum force. In addition to torpedo nets, the dams were protected by anti-aircraft guns positioned strategically around their perimeters. To evade these guns, the Lancaster bombers flew at extremely low altitudes, often just a few meters above the water. This tactic made it more challenging for the anti-aircraft guns to track and hit the bombers as they approached their targets. Combining these strategies with precise timing and coordination, the British were able to execute their daring mission with remarkable success. This feat not only crippled Germany's war effort, but also underscored the importance of innovative tactical planning in modern warfare. The combination of advanced engineering and meticulous operational planning showcased the British forces' ability to anticipate and respond to even the most formidable challenges. The success of the mission relied heavily on the ability to predict weather conditions with remarkable accuracy. Precise weather forecasting played a pivotal role in determining the timing and route selection for the mission. Meteorological data was closely monitored to anticipate any changes that could impact flight conditions. The ability to foresee wind patterns, cloud cover, and visibility ensured that the bombers could navigate through treacherous terrain without detection. This critical intelligence allowed the squadron to minimize exposure to enemy fire and maximize their chances of successfully breaching the dams. It is a testament to how environmental factors can dictate the course and outcome of strategic endeavors. As the Weimar Republic crumbled, the Ruhr area found itself at a strategic crossroads. Its extensive industrial infrastructure made it a critical target for military operations. Mass production presented its own set of hurdles. The bombs were massive, weighing approximately 9,250 pounds each, and required meticulous engineering to ensure reliability under combat conditions. Refinements were made to improve the bomb's stability and accuracy. By ensuring the bombs maintained a consistent spin rate and trajectory, Wallis could maximize their destructive potential. Understanding the evolution of production techniques behind the bouncing bombs provides a glimpse into the relentless pursuit of tactical superiority during wartime. To begin with, the Lancaster crews faced accuracy issues that could render the bombs ineffective. The bouncing bombs had to be released at exactly the right height and distance from the target dam to ensure they skipped across the water rather than sinking prematurely. Barnes-Wallis was aware of these challenges and provided crucial on-the-ground support during deployment. He devised a clever system to assist the pilots in achieving the necessary accuracy. A spotlight was installed at the water's edge, and a series of flares were set up along the water's surface. As the Lancasters approached their targets, the pilots would release the bombs at a specific point where the spotlight and flares intersected. This visual cue helped ensure that the bouncing bombs were released at the correct altitude and distance to achieve the desired skipping effect. To mitigate these risks, Wallis had designed a secondary backup system into the bombs themselves. In the event of a backspin failure, a small propeller-like mechanism would deploy and attempt to spin the bomb backward manually. Their story serves as a testament to the ingenuity and resolve required in the face of insurmountable challenges during wartime. As the Allied forces prepared to launch their daring operation, the German intelligence machine was already in motion. The stakes were high. The dams that provided crucial water supplies and electricity were now potential targets. Anticipating the Allies' plans, German intelligence stepped up their surveillance measures around the dams. Enhanced patrols and advanced sensors were deployed to monitor any unusual activities. Additionally, defensive structures were rapidly constructed around the strategic points of the dams. These included reinforced concrete barriers and sophisticated anti-aircraft systems designed to thwart any incoming attacks. But as the Allied forces advanced their innovative technology, the cat-and-mouse game intensified. German intelligence continuously refined their strategies to stay one step ahead of potential threats. The effort to protect these critical infrastructure points was immense, requiring constant vigilance and quick adaptation to any new information or suspected enemy movements. Yet, the sheer audacity of the Allied mission meant that despite these measures, the German intelligence machine could not entirely eliminate the element of surprise. This set the stage for a high-stakes confrontation that would determine the course of critical World War II operations. The cat-and-mouse game between Allied offensives and German defences continued to unfold in the shadows of these towering structures. The immediate effects on German civilian life were catastrophic. Floodwaters surged downstream with unstoppable force, claiming hundreds of lives and leaving thousands homeless. In the Ruhr area alone, approximately 1,300 people perished in the initial floods, with many more displaced. The devastation extended beyond human lives to critical infrastructure and industrial facilities. Local authorities were quickly overwhelmed by the scale of the disaster. With communications and transportation systems crippled, coordinating rescue efforts became a Herculean task. The psychological impact was equally profound. Fear and uncertainty gripped the civilian population as they grappled with the sudden loss of homes, livelihoods, and loved ones. Relocation efforts saw communities rebuilt further from riverbanks, with new safety measures and dam designs implemented to prevent future catastrophes. In the wake of the operation, German civilians faced not only material loss, but also an erosion of trust in their leadership and the stability of their lives. Despite the efforts to rebuild and regain normalcy, the memory of that fateful night lingered as a chilling reminder of war's far-reaching consequences. The innovation demonstrated in this daring operation would pave the way for future military strategies and technological advancements. As World War II gave way to the Cold War and beyond, precision weaponry became a cornerstone of military strategy. This innovation led to the development of smart bombs and cruise missiles, weapons capable of striking specific targets with high accuracy. The guided missile systems, first deployed during the Vietnam War, have since become staples in modern military arsenals. The precision and efficiency of these weapons not only minimize collateral damage, but also enhance the tactical advantages in conflict situations. These innovations serve as a testament to how wartime necessity can drive technological progress and shape the future of military strategy. Even as decades pass, the echoes of that daring night continue to influence military strategies worldwide. But for these bombs to be effective, precise timing mechanisms were crucial. The mission's success hinged on the delicate balance of physics and engineering. The precision required to make these bombs effective highlights the ingenuity behind their design. The spin ensured that they followed a predictable path across the water. But it wasn't just about the spin, the timing mechanism inside the bombs was equally critical. The bombs had to explode at a precise height and speed to breach the dams. The mission's success was not just about the explosive force, it was about the precise orchestration of these technological marvels. The timing mechanisms inside these bombs were a testament to human ingenuity under pressure. They turned what could have been a simple explosive device into a sophisticated weapon. The bouncing bombs were more than just weapons. They were a symbol of human creativity pushed to its limits in the face of adversity. And, as we marvel at their ingenious design, we are reminded that even the most seemingly impossible challenges can be overcome with the right blend of science and determination. The echoes of that night continue to resonate, not just for their military significance, but for the technological marvels they brought into existence. Hydrographers collected detailed data on the water levels, river flows, and reservoir capacities of potential dam targets. This information was essential for predicting how a breach would affect downstream regions and ensuring that the mission's impact was maximized. The Möhne Dam hydropower project, a WWII endeavor, was one such target that underwent scrutiny. Planners needed to know not only the structural integrity of the dam, but also the topographical features surrounding it. Accurate targeting was vital to avoid civilian casualties and ensure that the operation's benefits were focused on military objectives. By leveraging hydrographic data, the planning team could anticipate flood patterns and allocate resources effectively. The mission's unique demands necessitated the use of unconventional techniques and equipment. One key challenge was navigating at extremely low altitudes to evade German radar. Training involved flying over water bodies at heights as low as 60 feet. This helped crews become accustomed to the visual cues and conditions they would encounter during their daring nighttime raids. Another critical aspect was mastering the precise timing and angle of bomb release. The upkeep bombs needed to be dropped from a specific height and speed to bounce across the water's surface and hit their targets. Extensive practice runs were conducted to perfect this maneuver. To simulate the conditions of the actual mission, the crews often trained at night under low visibility. The importance of these training methods was evident in the precision and effectiveness with which the operation was executed, illustrating the rigorous preparation required for such a high-risk operation. The trailers needed to be capable of maintaining stability at high speeds, as the convoy would have to travel long distances across uneven terrain. This was especially critical given the sensitive nature of the cargo. One innovative solution was to use large aircraft to airlift some of the bombs directly to their destination. However, this method could only be used for a limited number of bombs due to space constraints. For the majority of the bombs, ground transportation remained the primary mode. The trailers carrying these heavy loads had to navigate narrow roads and bridges, which added another layer of complexity. To mitigate risks, specially trained drivers were selected for the task. These drivers underwent rigorous training to ensure they could handle the unusual loads and maintain safety throughout the journey. Despite these precautions, the mission was fraught with tension. Every mile brought the convoy closer to its destination, where the bombs would be deployed in a daring raid against German dams. The successful transportation of these bouncing bombs underscores the meticulous planning and execution required for such an unprecedented operation. As the Lancaster bombers began their perilous journey to Germany, the British planners were well aware of the formidable defensive measures protecting the German dams. At each dam site, anti-aircraft guns were strategically positioned to detect and intercept incoming attacks. Searchlights scanned the skies, ready to illuminate any intruders, alerting the gunners to their presence. Early warning systems, manned by vigilant observers, provided an additional layer of surveillance, ensuring that any approaching threat would be quickly detected and reported. The mission required such precision that pilots had to navigate by sighting landmarks on the ground, relying solely on their skill and the darkness of night to guide them safely to their targets. As the waters receded and the damage was assessed, it became clear that the bold planning and execution of this mission had changed the course of the war, underscoring the importance of audacious tactics in overcoming seemingly insurmountable obstacles. The Möhne Dam, one of the primary targets, was a formidable structure located in the Ruhr Valley. This embankment dam stood at an impressive height of 40 meters and held back a vast reservoir capable of storing approximately 136 million cubic meters of water. To breach this dam effectively, Allied forces conducted detailed hydrographic surveys. These studies included depth measurements that revealed the reservoir's complex topography and water flow dynamics. The Eder Dam, another crucial target, presented a different set of challenges. This concrete gravity dam, standing 42 meters high, was designed to withstand significant pressure from the reservoir it held. The hydrographic studies of the Eder Dam were no less thorough. Geological compositions and structural assessments were crucial in understanding the dam's vulnerabilities. Allied engineers also took into account the depth of water in the reservoirs and the dynamics of water flow, ensuring that their innovative bouncing bombs could achieve maximum impact. These hydrographic studies were not merely academic exercises, they formed the backbone of the mission's strategy. By understanding the intricate details of these dams, the Allied forces could pinpoint their weakest points. This audacious operation demonstrated the power of meticulous preparation and scientific rigor in military strategy. The hydrographic studies were instrumental in selecting targets that maximized the mission's impact. While the precision of hydrographic studies was critical, the deployment of bouncing bombs presented a wholly new set of challenges. The bouncing bombs were revolutionary in design, but required meticulous handling and storage conditions to ensure their effectiveness upon release. Storing the bombs meant keeping them at a constant temperature of 50 degrees Fahrenheit, 10 degrees Celsius. Any deviation could affect their performance. This was no easy task, considering the bombs were 9,250 pounds each, the weight of an average car. This spinning action simulated the effect of dropping from a greater height, essential for the bomb's skipping and sinking mechanism to work correctly. The release point was equally crucial. Bombs had to be dropped at a precise height of 60 feet, 18 meters, and an angle calculated to ensure they skipped across the water's surface. Coordinating the flight paths of multiple Lancasters over enemy territory at such a low altitude was a dangerous and complex operation. The entire mission relied on split-second timing and flawless execution. Even the slightest deviation could jeopardize the mission's success. Despite these challenges, the precision planning and deployment of bouncing bombs proved pivotal in disrupting Germany's war infrastructure. This audacious operation underscored the profound impact that innovative technology and meticulous planning could have on the war effort. Comprehensive hydrological reports on the target dams were crucial for selecting optimal attack sites. These reports detailed water levels at the time of the mission, providing critical data for the success of the operation. The impact of potential breaches on downstream areas was meticulously analysed to understand the tactical implications. This analysis aided in predicting the extent of flooding and its potential consequences on civilian populations. Such calculations were vital for minimizing collateral damage while maximizing strategic impact. This meticulous hydrological analysis underscored the profound importance of scientific data in military strategy. The success of breaching German dams with innovative technology set a new precedent for military operations. Military planners now understood that strategic targets could be taken down with unconventional methods. This realization led to a significant shift in dam breaching strategies. Scientists and engineers began to explore new ways to disrupt enemy infrastructure using similar, precision-guided weapons. These advancements paved the way for more sophisticated military operations in later conflicts. For instance, during the Vietnam War, the US used similar precision-guided bombs to target key enemy infrastructure. The breach of the Möhne Dam was particularly devastating. This significant industrial site supplied water for various critical industries, including steel production and coal mining. the sudden flood displaced thousands of people and severely disrupted supply chains, bringing production to a halt. The cascading effects of these dam breaches extended beyond immediate flooding. Steel production, a cornerstone of Germany's war effort, ground to a halt as furnaces required massive amounts of water for cooling. Coal mining operations, which heavily relied on water for both extraction and processing, were also severely impacted. The loss of water supply forced mines to shut down temporarily, further exacerbating Germany's fuel crisis. Perhaps most significantly, the destruction of key dams hindered Germany's ability to transport critical resources. With waterways disrupted and infrastructure damaged, supply chains for military equipment and munitions were severely compromised. This technology was crucial in navigating through German-occupied territory at night. The Lancaster bombers used H2S radar, which sent pulses of radio waves towards the ground. These signals would bounce off the surface and return to the aircraft's receiver, creating a detailed map of the terrain below. This allowed pilots to identify key features such as lakes and rivers, which were otherwise invisible in the darkness. The radar system also helped avoid detection by German defences, as it operated on a different frequency than their radars. Moreover, the H2S radar's ability to detect changes in elevation allowed pilots to navigate the complex terrain with precision. This technological advantage played a pivotal role in the mission's success, as pilots could accurately target and breach the dams. Without this advanced tool, navigating the dark skies over enemy territory would have been an insurmountable challenge. Ultimately, the effective use of radar technology underscores its critical role in the Allies' strategic victory during World War II. As we look back on this historic operation, it is clear that the fusion of technological prowess and tactical ingenuity can change the tide of war. German engineers bolstered the dams with robust anti-aircraft defences, aiming to deter any potential aerial assaults. These fortifications included heavy machine guns and advanced detection systems designed to thwart British bombers. Additionally, physical barriers such as steel nets were deployed across the surface of the dams. These nets were intended to prevent the bouncing bombs from reaching their targets unimpeded. But perhaps the most sophisticated defense was Germany's early warning system. This network of lookouts and sensors kept constant vigil over the dams, alerting authorities to any incoming threats. The Lancaster bombers flew at extremely low altitudes to evade radar detection, a tactic that caught the Germans off guard. This daring operation highlighted the British Royal Air Force's ingenuity and resolve, demonstrating how strategic planning and cutting-edge technology could overcome even the most fortified defences. The Lancasters had to carry the bouncing bombs, which were so large and unconventional that they required significant adjustments to the aircraft. One of the most critical modifications was to the bomb bay doors. These were adjusted to open wider and faster than normal, to allow the bombs to be released at precisely the right moment. This spinning motion ensured that the bombs would bounce across the water's surface and skip beneath the torpedo nets protecting the dams. Moreover, extra equipment was added to stabilize the aircraft while it flew at extremely low altitudes over enemy territory. The pilots had to fly just 60 feet above the water's surface to avoid detection by German radar systems. This precision required not only technical prowess, but also immense skill and courage from the aircrew. The modifications to these Lancaster bombers stood as a testament to British ingenuity and resolve in the face of formidable challenges. Repair teams worked around the clock to shore up the weakened sections with temporary reinforcements. While these measures were effective in stemming the immediate crisis, the long-term repair work presented significant challenges. The Allies faced difficulties in monitoring these repairs due to the ongoing conflict and limited surveillance capabilities. Without precise information on the extent of repairs, Allied strategists had to account for various scenarios. This uncertainty led to strategic shifts as the Allies adapted their plans to accommodate potential risks from the repaired dams. The repairs of the German dams served as a constant reminder of the resilience and adaptability of both sides in this ongoing conflict. At Recolver Towers, an extensive series of tests were conducted to refine the precision and reliability of a revolutionary weapon, the bouncing bomb. Prototype testing at Recolver Towers was meticulous, involving various altitudes and speeds to ensure the bombs behaved as intended under different conditions. Telemetry played a crucial role in recording data from each test run, allowing engineers to analyze the bomb's performance in detail. The bomb's spinning action, combined with their careful calibration, made them lethal weapons capable of breaching even the sturdiest dams. The meticulous planning and testing of these weapons changed the course of World War II, highlighting the audacious tactics employed to disrupt enemy infrastructure. The operation known as Operation Chastise was no mere gamble. It was a meticulously planned assault that relied heavily on Allied intelligence to ensure its success. By focusing on specific targets such as dams and reservoirs, the Allies could achieve significant disruptions with relatively little effort. This approach was later replicated in other campaigns, most notably in the targeting of German industrial facilities. The raid set a precedent for future military operations, emphasizing the importance of meticulous planning and intelligence gathering in executing successful strategic attacks. The ability to surgically target key infrastructure deep within enemy territory signaled a new era of warfare. For the Allies, this meant reassessing their approach to future operations, emphasizing meticulous planning and advanced technology. One of the most notable changes was the increased focus on intelligence gathering and detailed reconnaissance. The Allies recognized that accurate information was crucial for successful strikes, leading to significant investments in espionage and surveillance technologies. The emphasis on careful planning and the integration of advanced technologies continued to shape Allied operations throughout the war. This evolution in strategic thinking played a crucial role in turning the tide against Germany. The broader implications of this mission were profound. It not only changed the course of World War II, but also set a new standard for future military operations, highlighting the importance of careful planning and technological innovation. Barnes Wallis, the inventor behind this innovative technology, understood that thorough testing was essential to ensure its efficacy and reliability. The first prototypes were tested in a mock-up environment that replicated the conditions of the German dams as closely as possible. Wallis and his team faced significant challenges during these early trials, with many prototypes failing to perform as expected. They found that the bombs often spun off course or failed to skip across the water correctly, which could have rendered them ineffective against the dams. Determined to refine their design, Wallis and his engineers made several innovations based on these initial setbacks. In the early years of World War II, a new kind of warfare emerged: precision bombing aimed at strategic targets deep within enemy territory. One of the most innovative and daring tactics in this arsenal was dam breaching. The ability to cripple an enemy's infrastructure by targeting their water supply became a critical military strategy. Recognizing this limitation, engineers on both sides began to develop more sophisticated tools. The Germans pioneered the use of high-velocity explosive charges that could penetrate concrete barriers. In the aftermath of the operation, both Allied and Axis forces redoubled their efforts in developing advanced bombing technologies, leading to further innovations in precision warfare. To validate its effectiveness, Wallis first conducted experiments using scale models in a water tank. These trials allowed engineers to observe the bomb's behavior and refine its design before moving on to larger-scale testing. The Recolver Towers in Kent, England, served as a crucial testing ground for full-scale trials of the bouncing bomb. Here, Wallis and his team conducted extensive tests to ensure the bomb's reliability under various conditions. The towers provided a realistic environment for observing how the bomb would perform in actual operational conditions. Despite facing numerous challenges, such as maintaining the bomb's spin and ensuring accurate release, Wallis's team meticulously worked through each issue. This meticulous preparation underscores the critical role prototype testing played in the operation's success, highlighting the importance of rigorous planning and execution in precision warfare. One of the key components was the stabilizing automatic bomb sight. which used a complex system of gyroscopes and pendulums to maintain the bomb's trajectory despite any deviations in the aircraft's path. This ensured that even if the plane encountered turbulence or maneuvered evasively, the bomb would still follow its predetermined course. Another crucial element was the light signaling projector, which projected a series of flashing lights onto the water's surface to create a visual reference point for the pilots. This helped them accurately gauge their distance and altitude relative to the dam. This spinning was achieved using a device known as the upkeep spinner, which wound up the bomb like a top just before it was released. This required not only mechanical precision, but also careful timing to ensure that the bomb reached its target at the correct speed and angle. Barnes-Wallis knew that breaching the German dams would be no easy task. The Germans had fortified their dams with layers of sophisticated defences to protect against exactly such an attack. Each dam was surrounded by anti-aircraft artillery that could quickly intercept any incoming bombers. Additionally, underwater nets were installed to prevent the bombs from reaching their targets. The operation planners had to carefully map out these defensive measures and devise a strategy that could overcome them. This required meticulous planning and precise execution. To counter the anti-aircraft artillery, the bombers would need to fly at extremely low altitudes to avoid detection. This would be risky, but necessary to avoid being shot down. The underwater nets pose an even greater challenge. The bombs needed to bounce over these nets and into the dams. This required precise timing and an innovative design. Wallis designed the upkeep bomb with a spinning mechanism that would cause it to bounce across the water and over the nets before sinking into position and exploding. The careful coordination between flying at low altitudes and precise timing ensured that despite these formidable defences, the mission stood a chance of success.